So delta H relates to the molar amounts in the balanced chemical equation that's listed. So delta H here minus 393.5, that's for every mole of carbon that's released, that's reacted, sorry. If I burn 2 moles of carbon, how much energy am I going to get? Twice as much, right? So if I multiply the coefficients by a factor of 2, I multiply delta H by a factor of 2. If I multiply by 5, I multiply by 5. If I divide by 3, I divide by 3. Okay? If the reaction is reversed, then you change the sign of delta H. Because if this is an exothermic reaction, then running the reaction backwards must be endothermic. So you think about the ice cube. Melting the ice cube absorbs energy, freezing the water back into the ice cube releases energy. It's the same amount of energy. It's just going in a different direction. So I wrote this reaction backwards. So delta H is the same number, but I changed the sign. This is Hess's law. The change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. This takes advantage of enthalpy being a state function. Doesn't matter how you get there, just the net difference between. So if I have a reaction A plus 2B going to 2D, and I want to know delta H for that, but I don't know what it is. If I can come up with other reactions where I know delta H and combine them to form the reaction I'm interested in, I can do that. So what we're doing here is we're saying, well, this reaction, A plus 2B forming C, that's delta H1. So A plus 2B going to C is this amount. And C going to 2D is delta H2. Now that would be negative, right? So A plus 2B going to 2D, you can get that by adding these two chemical equations. The C that is made here gets used up over there. So just like the electrons when we balance redox reactions, A plus 2B makes 2D. So then here, my delta H is the sum of the delta H's. Okay? We can think of this in terms of altitude. So here we have our mountain, and we're starting up here on top of the mountain, and we're going to end up down here. And we want to know what the altitude change is. Well, we have no way of measuring it as we're walking down. But this guy could get picked up by a helicopter, and the helicopter has an altimeter in it, and it can measure altitude. So it goes from here to here. We can figure out what that change in altitude is. And then the helicopter comes back down all the way to the ground, and we can figure out what that change in altitude is. The change in altitude from the beginning, starting on top of the mountain, to the end is the sum of those. One's positive, one's negative. It's the same concept. Any questions? So there's three rules about dealing with the delta H's. If you multiply the equation, you multiply delta H. If you change the direction of the reaction, you change the sign on delta H. And you can add reactions together, and then you add up the delta H's. Let's do an example. Find delta H for this reaction. Use these reactions with known delta H's. So we've got this information here, these three reactions and their delta H's. But what we want to find is this guy up here. So we have to figure out how we can combine these chemical equations to get that one. There's different ways to approach this. I'm just going to start at the beginning. I want N2O to be a reactant. So do any of these reactions have N2O as a reactant? Yeah, this one does. So I could write that one out. Okay, well, I've got 2 N2O going to 2 N2 plus O2. And did I do anything to the chemical equation? Reverse it or multiply it? Nope. So delta H is just the same. I'm just going to copy it down. So there's N2O, and here I've got 2 N2O. So I've got twice as much as I need. Do you want to fix it now or fix it later? I can't. Somebody say it loud. Fix it now. Okay. So I don't want 2 of those. I only want 1. How do I make a 2 into a 1? Divide by 2. Right? So I'm going to take this whole thing, including delta H, and divide by 2. So then this 2 becomes a 1. This 2 becomes a 1. And this becomes a 1/2. It's okay. And then I'm going to take this and divide by 2. Because that's what I did to the equation. Because if I react half as much, I'm going to have half as much energy. Okay, so now I've got my first reactant. The second reactant I want is NO2. So I'm looking, there's NO2, but it's a product. So I need to write that equation backwards. So NO2, it's 2 NO2. It's going to go to 2 NO plus O2. So I took the equation and wrote it backwards. What do I do to delta H? Change the sign. So this is going to be plus 113.1 kilojoules. We got the same problem here. This is 2 NO2s, and I only want 1. So I'm going to divide by 2 again. Divide by 2, divide by 2, divide by 2, so that's 1/2. Then this one, divide by 2. So if I added these together right now, I'd have N2O plus NO2. So the left side is all good. But on the right side, I've got NO, but I also have N2 and O2, and I don't want those. So I must need to use this other equation that I'm given. This has N2 and O2 on the left, and that would help me to get rid of these. So I'm going to write that one in as written. N2 plus O2 forming 2NO. And I'm not doing anything to the equation, so I'm not going to do anything to delta H. Now let's see what happens. We're going to add these 3 equations together, and I see that I've got 1 mole of nitrogen being produced here and 1 mole of nitrogen being used up. So those cancel out. Here I've got 1/2 mole and 1/2 mole of oxygen. Together that's 1 mole, and there's 1 mole of oxygen. So as the oxygen gets made, it gets used up, and so it doesn't show up in the final reaction equation. Now what I have left is N2O gas plus NO2. So many O's and 2's and N's. It's a bit confusing. And over here, the only product I have left is NO gas, but there's 3 of them. I've got 2 here and 1 there. 3. And that matches up with the equation at the top. So to find delta H for that reaction, I'm going to take this divided by 2 and add this divided by 2 and add that. So I have negative 163.2 divided by 2 plus 113.1 divided by 2 plus 182.6. $157.55 kilojoules. All of those had 1 decimal place. This should be rounded to 1 decimal place. So the heat of reaction for this as written is 157.6 kilojoules. Any questions?